Baranger. Harold, actually for him it's a return to Harvard. He got his undergrad at Harvard and has since been for master and PhD Cornell, has done some postdoctoral work in Paris, and since '99 he is a professor at Duke University. Harold is working, when I kind of roughly read the topics, what came to my mind is quantum optics of interacting electrons. In his own words, quantum coherence of solids, particularly nanoscale systems. And that's what we will hear today. Harold has, of course, a number of prizes. Let me just tell you, he's a fellow of the APS, and he had a chair d'excellence of the Nanoscience Foundation in Grenoble for 3 years. He has a really, really impressive body of publications on these things. So let us welcome Harold on waveguides in QED, or waveguides QED. So, okay, thank you.
Am I on?
Yes.
Yeah, is that good? Well, thank you very much for the introduction. It's a pleasure to be here at Harvard again. So my background, as I said, is in condensed matter theory, mostly quantum transport and nanostructures. But more recently, I've been working on some quantum optics problems, and that's what I want to tell you about today. So I'll be talking about the system I'll be talking about consists of one-dimensional bosons, which can be photons, plasmons, whatever your favorite boson is. I'll have in mind photons. Coupled to two-level systems, which can be an atom, a qubit, quantum dot, etc. And my main interest here is to look at the correlations among the photons which are induced by this coupling between light and matter. And I'll start out with some motivation from various fields, like so. One of the nicest parts about working in this field is that there have been really enormous experimental progress in the last 10 years. And not just in one area, but in several different platforms. So I want to just briefly tell you, point out what a few of those platforms are. And then we'll get into some results. The sort of foundational result is that one has these photon-photon correlated states, with which you can then use to do various things. And I'll show you one, which is photon capture into a bound state in the continuum. And then in the second part of the talk, I'll move to considering ultra-strong coupling, which is just becoming available in the superconducting qubit platform, and talk about sort of photon production, how the number of photons is increased in scattering processes in the ultra-strong regime. And then I'll end. There's been a number of reviews, 3 or 4, that have come out in the last year or so, and I'm listing one of them here for your information. Okay, so the first motivation from quantum optics, you know that there's this classic problem in quantum optics of cavity QED, in which you have an atom coupled to a mode in a single mode in a cavity. The states of the system consist of the harmonic oscillator states when the system is in the ground state, and the harmonic oscillator states when the system is in the excited state, and then they're coupled in this James-Cumming Hamiltonian, which leads to a splitting. And that means if you try and put in a photon from the outside, that you can put in one photon, but there isn't a state for the second. So there's a kind of a photon blockade, and that you can view as an effective interaction between the photons. Now, this is a zero-dimensional system because it has a discrete spectrum, and one question I want to address is, does coupling to a continuum of modes, a one-dimensional continuum of modes, bring in something new? Now, once you have interactions among your photons, this photon blockade, it's natural to think of an extended system in which this interaction occurs. And there's been work by a number of groups in different directions on this. I'm just showing you one example here from Koch and Leher, in which they considered a honeycomb lattice with this Bose-Hubbard model, this photon blockade system at each node. And they noted that then you can get interesting many-body states, in particular a superfluid state and a Mott insulator state, like so. And finally, there's a lot of interest in this system from quantum information point of view. Again, from sort of different kinds of things, routers, photon transistor. Again, I've chosen one example here, which is suppose one has a set of quantum nodes and you want to communicate between them. Perhaps these are nearby and you just want to increase your quantum computation power. Perhaps they're far away and you actually want to communicate some quantum information from one place to another. Now, within cavity QED, there's a scheme that has been developed for doing that, whereby you can move your quantum information into the cavity mode. It leaks out along the fiber, and then with the appropriate pulse, put it back into your matter, your quantum node here. And this relies on having these cavities, which, on the other hand, are somewhat slow if kappa isn't large. And one thing that I want to address is there a cavity-free way to do this kind of thing? Okay, so here's my waveguide and just a little bit of background terminology. So I have my two-level system. The waveguide is kind of faint, but hopefully you can see it right there. The two-level system has various decay processes. It can decay into the waveguide. That rate is gamma. That's the one we're interested in. Gamma prime is the rate into all the other possible degrees of freedom, which we are not interested in. And so we certainly want to work in the regime where that ratio is large. And in fact, most of the results I'll show you today are in the limit when gamma prime is equal to 0, but we have done some work for finite loss as well. Dipole coupling, if I write it in terms of the two-level system states and the bosons in the waveguide, it looks like this. For this first part of the talk, I'll make the rotating wave approximation in which you neglect the terms in which a photon is created and the two-level system is excited. And that's an approximation which is valid when the width over the level splitting is much less than 1. So the experimental systems, there's quite a few groups working on these days, and so I've chosen just 3 to show you. Certainly within the atomic physics community, there's a lot of interest. For instance, one system is having a dielectric waveguide, like so, and then positioning an atom within the dielectric or next to the dielectric waveguide. This is an example from the Caltech group. Then you can do a scattering experiment on that. A slight variation on that is to use a quantum dot instead of the atom as your two-level system. And for example, you could use a defect in a photonic crystal as the one-dimensional waveguide. So here's a sketch from this paper from the Lodal group, and you can see that you have a photonic crystal with this line defect which corresponds to the waveguide, and this is the quantum dot there. And finally, as a condensed matter physicist, the thing which sort of attracted me initially was this system of having a superconducting qubit coupled to a microwave transmission line. So this is a picture from the Chalmers group. This is the microwave transmission line. The light here is metal and it's grounded. And in the middle, that line there is the line on which the voltage will be traveling up and down, as it were. And in here we have a transpon qubit. You can see the big capacitor associated with the transpon qubit and the Jefferson junction, which you can't really see, but it's right in the middle of it there. And again, the idea is to do transmission, or in this case reflection, measurements from this system. Okay, so what's the basic idea kind of at the simplest level? So here it is. Suppose the basic idea is just to notice that the scattering by a two-level system depends on its state. Right? So if I have two photons coming along that are resonant with my two-level system, the first one excites the two-level system, the second one comes along, it can't excite the two-level system, right? But as a result, it can go through, it can be transmitted, and it can cause a stimulated emission. If it does that, then in the transmitted channel, those two photons become correlated. This is supposed to be a sketch of the photon wave function in the relative coordinate here. And as a result, kind of like we saw in the photon blockade, here also in one dimension, you have an interaction, a correlation generated between the photons. So how do we describe this? Well, we could take a continuum model. I'll have my 1D continuum of bosons where I've taken a linearized spectrum, right-going bosons, left-going bosons. I have my two-level system with the possibility of having some loss, and this is the coupling then, destroying a photon and exciting the two-level system. Now, we're going to consider strong coupling in the sense that gamma over gamma prime is large, but not ultra-strong. And by that I mean that we're going to continue to neglect these terms here, which involve a double excitation of the system. And in that sense, so the number of excitations is conserved, and in that sense, in a condensed matter language, there's no Kondo effects which are included. And if you had asked me some time ago if I take spin boson model and throw out the Kondo effects, is anything interesting left? I would have said no. And indeed, for the ground state, that's true, right? The ground state of this Hamiltonian is totally boring. The two-level system is in the ground state and there aren't any photons. But what I didn't realize is that if you go to the non-equilibrium case, and in particular if you consider injecting pulses into the system, then indeed this interaction here can lead to interesting photon correlations. So there's quite a few groups working on this, and I've listed a few of them here. And I want to particularly note the early work in the 80s, back in the former Soviet Union, of Jefferson, that anticipated a lot of what was learned in the early, well, say about 10 years ago. Okay, so suppose I go about solving this, solving for the wave function. We're interested in the few photon limit, so we'll start with one photon. And this is quite a straightforward problem. I can write down my wave function as either there's a photon in the waveguide, or there's an excitation in my qubit here, and you put that into the Schrodinger equation, max true boundary conditions, just like we were all taught in our graduate quantum mechanics class, and you get your transmission amplitude. You go on to the two excitation channel. So you have a wave function with two photons, a wave function with one photon in an excited state, and now you go to make your plane wave solution, and it can't be done. There's no solution to the Schrodinger equation built from just this form here. And in fact, what's needed is an additional term in which there's an exponential correlation in the relative coordinate. And the strength of that correlation, you can see, is related to the coupling to the qubit. And so it becomes interesting when the coupling is strong. Right? So far you can see this is quite simple physics. It could have been done quite some time ago. I think the reason it wasn't is that the experimental systems didn't exist in which you could have this large coupling and so make this strong correlation among the photons. Just to illustrate that, here's the two photon wave function for scattering from a single qubit from an infinite waveguide. So this is the psi squared as a function of the energy of k vector of the first photon, detuned from resonance, and the detuning of the second photon from resonance. And of course, by conservation of energy, this has to lie on a diagonal line like so. Right? the two photons came in with energy k naught. But you can see along that line there's rather distributed intensity along that line. And there's an entanglement then in the energy. There's inelastic scattering, first of all, the energy changes. And there's entanglement between the energy of the first and the second photon. You can characterize the correlation by looking at the photon-photon correlation function, G2. So this is just the intensity correlation function, normalized by the density. And with this normalization, if G2 is equal to 1, that's an uncorrelated state. So again, here for a single qubit in an infinite waveguide, this is G2 for the transmission. And you see that as for the simple hand-waving argument I gave, there's bunching of the photons. That is, G2 of 0 is bigger than 1, so that the photons tend to come together. While in reflection, there's anti-bunching of the photons. And indeed, the fact that this G2 at t equals 0 is equal to 0 is required if I have a single qubit, because as a qubit can only reflect one photon at the time. And in the reflection channel, of course, every photon must come from the qubit. So here's an example of a photon-photon correlation in a slightly more complicated system. So this is a semi-infinite waveguide in which we put an atom, some distance from the mirror, an atom in front of the mirror. And we've calculated the correlation function for two different lengths. For a short length, that's the red line. Notice that G2 of 0 is bigger than 0, much bigger than 0. And that's allowed now because I can have a photon reflected from the mirror at the same time that a photon is emitted from the qubit. So I can have bunching. As I make this distance large, the effect of this time delay comes into play. And in particular, one gets a very big difference between the result from doing a Markovian approximation, which is the red line, and the full calculation, including the non-Markovian effects, which is the blue dots. We've done some further characterization of non-Markovianity in this system together with my collaborator from Italy, Francesco Ciccarello, in this preprint. So here's an experiment in the superconducting waveguide system. One of the early experiments of G2. G2 is a function of time, and you can see indeed that they see the bunching in transmission like so. Okay, but suppose I want to do a better job of characterizing the statistics, the correlation of these photons. So I want to do the full photon counting statistics. And that's because G2 tells you some information, but hardly all information about whether there's bunching or anti-bunching. One would like to know if the photons are coming out in groups, or whether they're evenly spaced, or what. And to tackle this problem, one could, of course, calculate the higher moments of the distribution of the intensity, but that's a very difficult way to go. What we chose instead to do was a quantum jump approach based on input-output theory, in which one describes the single photon events at the output. So let me sketch how that works. So you write a master equation for the reduced density matrix of the qubit, or qubits, if there's two of them, like so. And you find typically one would find then a master equation of this form that has a Hamiltonian part, which has not only the Hamiltonian of the qubit, but also the driving. This alpha k here is the driving of our input coherent state. And you have a Lindblad form for the dissipated part, for the jump part. And then it's known that one can solve, one way to solve this equation is to treat it stochastically, so as a stochastic Schrodinger equation, in which I have in which I produce then an ensemble of pure states, and it's by averaging over those pure states that I produce this reduced density matrix here. This has the advantage that you're producing then a possible history with time signature of when these events occur. And indeed, the quantum jumps associated with the decaying of the qubit have been observed experimentally. But that's not quite what we want, right? We want the quantum jumps associated with photon detection. So we need to use a different jump operator which involves an interference between the light coming out of the qubit and the input photonic field. The structure that you get is exactly the same as before. You get a Lindblad form with this new jump operator, and then the stochastic treatment in terms of quantum jumps is also the same. So here, for example, is an output of a quantum jump simulation. I'm showing you the excited state population of the qubit as a function of time. And you can see there's a nice smooth part, which is the unitary Hamiltonian evolution. And then there's these sharp jumps. Each one of those jumps corresponds to detection of a photon. And we've labeled them, in blue up here. These are the jumps which correspond to transmitted photons. And these are the jumps which correspond to reflected photons. So you see, I get a time series, right, of all of the photon events. So then I can look at any photon statistic that I want. Notice that there's a funny thing about these jumps. Normally, one would expect that the jumps, since they're related to the dissipative part, involve jumps down. But here I also have jumps up, particularly associated with the transmitted photons. This is the back action of detecting that photon. If I detect a photon in transmission, then I know the qubit must have been in an excited state. And then it's decaying from those excited states that gives rise to the bunching. Because if my qubit starts with a high population in the excited state, the probability of having subsequent emission events, just of the normal sort, is quite high. Now, this excited state population isn't the only thing you can calculate. So for instance, if I was doing this for 2 qubits, I could calculate the entanglement entropy between the 2 qubits. And again, you get a trace here which involves unitary evolution and jumps corresponding to the photon detection events. And you can see that at random places in time, you can produce states which are very highly entangled. So one statistic that's interesting to look at is, so I have this time series. Let's look at the time between sequential photons. So the so-called waiting time distribution. So that's shown here for a single qubit in transmission. You see this sharp peak near t equals 0. So that's the signature of the bunching, which you now see very clearly how many photons are involved and so on. And on the left for reflection, you can see the anti-bunching, the fact that there's a reduced probability of finding another photon in this region. Now for 2 qubits, so this is for 2 qubits separated by a quarter of a wavelength, this is the waiting time distribution that we get in reflection. And notice that it has both of those features, right? It has a bunching aspect here, right? And then there's this big hole where there's a suppression followed by a peak. So it has both a bunching and an anti-bunching aspect, which you can see quite clearly in this waiting time distribution. We also looked at the probability density of adjacent waiting times. So that's a 3-photon correlation here, right? So this is the time between the first 2 photons, the time between the second and the third, and you can see that there's 3 peaks in this distribution function. 2 of them correspond to 2 photons being close together and the other far apart, and then this peak in the center here corresponds to all 3 photons being separated from each other. And again, you get a much clearer picture of what's actually happening in your photon statistics than just numbering 2. Okay, so that's the basic, underlying phenomena of photon correlations, and now you can do various things with it. I want to show you one example which involves a photon capture into a bound state in the continuum. And this is work that's been done in collaboration with Francesco Ciccarello and two students, Giuseppe Calaho in Vienna, and Leo Fang, who was my student, and now is a postdoc at Brookhaven. So consider a semi-infinite waveguide with my qubit, and in the single photon properties, I have to remind you of a few things. So the first is that for a photon which is resonant with the qubit acts like a mirror. Okay? And a way to think about this is in transmission. So if I think in transmission, there's an amplitude for going straight past the qubit, and there's an amplitude for going into the qubit and coming back out. And when the photon is exactly on resonance, those two paths are out of phase, and you get destructive interference, and there's no transmission. And on the other hand, there's 100% reflection, and so my qubit acts as a mirror. So now, let me make this distance commensurate with a half wavelength. Then there's an exact bound state there, right? It's a bound state at the resonant frequency, so at the frequency which is degenerate with the continuum of the waveguide. And in the single photon sector, since it's an exact ground state, it's completely disconnected from any of the other states, and you can't fill it, doesn't show up in any spectroscopy, you don't see it. Now go to the multi-photon sector, two photon in particular is what we'll look at, and the idea is that the nonlinearity of the qubit will cause inelastic scattering, like we saw, and so make this bound state in the continuum accessible. So the idea is that I can have two photons injected, one stays in the BIC, and one is scattered out. So two photons in, one out. The distance has to be fairly large for it to make this work. You have to be in the non-Markovian regime. So let me just make a brief comment about that. In the Markovian regime, the fact that the coupling between the qubit and the waveguide changes, or is a function of the frequency of the photon, is neglected. And one just uses the coupling at the resonant frequency k0. So clearly then, if I put my qubit at a node, it's completely decoupled in n photon sector, and there's no effect. On the other hand, if it's far enough apart that I have a non-Markovian effect, so that this coupling varies, then there's the possibility for having this inelastic scattering. We look at two systems. The continuum system I've been telling you about, which we put two photons injected. We're using an exponential wave packet. And this results then in a partial differential equation you have to solve. It's a little bit tricky because there's a time delay coming from the bouncing from the mirror, which also causes a spatial non-locality. But that can be done. And the second system is just a coupled cavity array. So each of these is cavity array like so. This corresponds to a discretization of my continuum waveguide, if you like, a tight binding model. So the spectrum has this typical cosine K structure. Here's the Hamiltonian. And in this case, actually, we were injecting Gaussian wave packets. So here's, for example, the population in the qubit as a function of time. This is in the continuum case. So the population, there's some transient in which the population gets large. You're not surprised by that. But then there's this very long-lived part. Right? This is the typical lifetime of the qubit is 1, these units, so that's down here. And in fact, in our model, this never decays, right? Because the BIC never decays to the waveguide, this will last until there's some decay into some other degrees of freedom. And we can look at what the wave function looks like. So just in contrast, this is the case from the cavity. So this is psi squared, the intensity, the total photonic intensity as a function of x. And you can see here, this is the intensity that's trapped between the mirror and the qubit. This is a zoom in on here. In this case, we took the atomic frequency to be right in the center of the band, so that you get this characteristic oscillation as you go from one side to the next. You can look at the wave function in terms of both coordinates. So this is the photon wave function as a function of the two coordinates, Z1 and Z2. This is the initial state, a nice Gaussian product state. And this is at the end of the simulation. Again, this is the two photon part going out, the way in which I have two photons going out. And then this is the part of the wave function in which I have a photon trapped in the BIC, and the other photon is going away. And you can see again the characteristic oscillation of the BIC wave function in this coupled cavity array. So you can optimize the effect with the parameters. And there's three time scales in the problem. Right? There's the decay time, the natural decay time of the qubit. There's the time delay as the photon goes to the mirror and back. And there's the width of the incoming wave packet. And the effect is optimized when all three of those time scales are approximately the same. That's kind of an interesting result. So you can do this with two qubits as well. So again, I have my waveguide, I have the two qubits. There'll be an exact single photon bound state if these are spaced by half a wavelength here, like so. And of course, this bound state involves entanglement between the two qubits. So we can send in a pulse from the outside, have this inelastic scattering. This is the population that I showed you before, which is very long-lived. But now I also show the concurrence related to the entanglement between the two qubits. And it also has this transient regime, and then followed by a part where it's constant. So this is a way then of making entanglement between the two qubits, which is very long-lived, even though the qubits themselves, each individually, is still strongly coupled to the waveguide. You could then, for instance, at some much later time, tune one of the say the frequency of one of the qubits and let that photon out if you want. Okay, so now I'm going to switch gears to talking about the ultra-strong regime. And this is work that's done in collaboration with colleagues in Grenoble, in particular Serge Florent, Nicolas Gerhardt, and Nicolas Roch, who's an experimentalist. They're all at the Institut Néal. And so we go back to dipole coupling, and now I am not going to make the rotating wave approximation. And that means now that the ground state is no longer physical, right? The ground state has photons present. So in the ground state, near my two-level system, there's a cloud of photons which are interacting with the two-level system, which is flipping up and down, like so. And now we're going to do the same kind of scattering experiment. We'll send in a pulse. It'll be a coherent state, Gaussian pulse with n bar on average. N bar is the average number of photons. And it'll scatter off of this. We'll have an outgoing in the transmission channel and an outgoing in the reflected channel. And again, I'd like to say that we aren't the only people working on this. In particular, there's a number of papers from the Garcia-Ripoll group. There's early work from Karine Leher, and a linear response calculation from the group at Yale. Okay, so how are we going to tackle this? Well, first, what is the problem? So this is the spin boson model, right? I have a two-level system. I have bosons here, and they're coupling between the two-level system and the bosons. Now, I've switched my indices x and z to the condensed matter preferred labeling. So you can see I have sigma z being the operator interacting with the photons, but of course it's the same. And so we'll consider the model is characterized, at least the equilibrium model is characterized by the spectral density, and we take an ohmic spectral density. So it's linear in omega up to some cutoff omega c. and the strength, this strength is alpha, and the prefactors, the constant is chosen so that alpha equals 1 corresponds to the localization transition. So you know that in ultra strong, if the coupling is strong enough, then the qubit doesn't flip at all. They have a ground state which is exactly doubly degenerate, and the qubit is either on the left or the right. So this regime has become, is becoming available experimentally. So here's an example from the Grenoble group. And to get into the ultra-strong regime in the superconducting qubit waveguide system, what do you have to do? Well, the coupling between the qubit and the waveguide is related to the impedance of the waveguide. And of course, if you just use a microwave strip line, that impedance is 50 ohms, basically, very similar to the impedance of free space. So we have to increase the impedance of our transmission lines. And what they do is they make a chain of Josephson junctions, actually a chain of squids, so that the properties of the waveguide are tunable. So there's 5,000 squids in a line here, which makes a waveguide with an impedance of about 1/2 of the resistance quantum. So yeah, about 12 kiloohms. And then this is the qubit here. So we have these large capacitors because it's a transmon type qubit. And it's a charge qubit in which I have a box on this side and a box on that side, and I can have charge on either side, and that's my 1 and 0. And that, the dipole associated with moving the charge from here to there couples to the electric field, which is what gives you the large dipole coupling. Now, we're going to tackle this, so numerically, we're going to tackle this, and the method that we are developed and are using is to expand in multi-mode coherent states. So here's a multi-mode coherent state. I'll denote it like this. And you see it's an exponential of an AK dagger minus AK with certain amplitudes. So that's your familiar coherent state amplitude. And then you can see it's just a product of these operators creating a coherent states, product coherent state in various modes. And then the ansatz for our wave function, and we'll do a variational approach, is to have some coherence, one of these coherent states with a spin up, and a coherent state with a spin down, like so. Now, why coherent states? So here's kind of the physical motivation for that. So there's a transformation, a unitary transformation called the Polaron transformation, which has been known for a long time, decades, which if I apply to the Hamiltonian, I get the following. So I apply to the Hamiltonian. You eliminate the coupling term that I had before between the qubit and the Hamiltonian, the qubit and the wave and the photons, and instead put this term onto the qubit term, onto the solid state, what we would call the tunneling term, in which when the qubit shifts from the excited to the ground state, this is an operator which shifts the photons, the origin of the photons, in one direction or the other. You can think of this as X for my harmonic oscillators. So pictorially, I can have an energy surface for my upspin and an energy surface for my downspin, and I have a wave function, a coherent state, which is associated with each one of those, and I'm hopping back and forth. And of course, as I hop back and forth, I have to take into account the overlap between those two wave functions. As you go into the ultra-strong regime, okay, so this is here I did a Polaron transformation with a fixed amplitude, like so. And you can see there's a problem for an ohmic spectrum, because omega k goes down to 0, which means this blows up, and this is no longer well-defined or a good transformation. On the other hand, I can let this amplitude be a variational parameter. Okay? And if I do that, then I can obtain a result for the omic spin boson problem, which allows me to go, which makes sense for small alpha. Now, as the coupling gets larger, you have a problem in that in order to maintain some energy of flipping here, the two wave functions are made to overlap in this way, in a way which is not optimal. And what we realized is that it would be much better to build a wave function in which I had not only some amplitude in the desired space, in the desired part for the spin-up, but also some amplitude up here. Because then I would have overlap between the two wave functions, and I would have a better spin energy, even though I'm paying some elastic energy as a trade-off. And so, just for in this case of having just two polarons, you make the following ansatz: a spin up with the usual polaronic shift, and then plus some shift in the other direction, and just the negative of those for the downspin. That's required in order to maintain the spin symmetry. Okay, how well does it work? Well, very well indeed. So here, for instance, is the average sigma x, so if you like, the qubit splitting as a function of the coupling strength. And we know that as the coupling strength gets larger, the qubit splitting gets smaller and smaller and smaller. The red curve is the single polaron case. It does very well at the beginning, but then fails. And just putting in two polarons gives me the right qualitative behavior. The circles here are an exact numerical result from NRG. And there's also known an exact value from beta ansatz here, with which we agree pretty well. Furthermore, this is a systematic expansion. We've shown the inset here. As I put in more and more polaron, I can get closer and closer and closer to the exact result. So it looks like a pretty good way to go, because these sort of coherent states, these multi-node coherent states, are kind of a natural state for the bath when you're coupled to a two-level system. So what are we going to do then? We're going to make that ansatz and now make these variational parameters time-dependent. So it's known how to do that. This is called the Dirac-Frenkel variational principle. You have a Lagrange density related to your Hamiltonian density. With this variational wave function, then, this turns into time-dependent equations for those variational parameters. You find the Euler-Lagrange equations associated with those for all of the parameters in my system. So you have a whole bunch of differential equations, coupled differential equations that you have to solve. Now, one important point is that at the end of the scattering, so capital T is at the sort of end of the day when the photons of any scattered photons have gone far off, my state should be a product state between the ground state of the system, ground state of the qubit, and whatever is flowing away. This should be true in the single qubit case, right? There's no bound state in the continuum. There's a bunch of excited states. Everything's coupled to the waveguide. Surely I should decay to the qubit, and the surrounding photonic cloud should decay to the ground state in the long time limit. And so you just have to make sure that your variational wave function has the ability to produce this kind of product state at the end of the day. Okay, so what do we get for a result? So here it is. So this is just the spectrum, so just the energy of the photons which are coming out after this scattering experiment. Here on a large scale, so this is off-resonant excitation. Right? This is the qubit frequency that I put into the Hamiltonian, so the bare qubit frequency. This is the transmitted beam. You can see it's quite large because I'm detuned from the bare frequency, and this is the reflected beam here. And now we're going to zoom in, right? Because what I'm interested in is the inelastic scattering, not the elastic part. And what you see for the inelastic scattering, so the total inelastic scattering is this gray here. And then we've decomposed it into the 2-photon part, the 3-photon part, and the 4-photon part, like so. So 2 things in particular to notice. One is that the peak of the inelastic scattering is not at the bare frequency, right? It's at a renormalized frequency, which is smaller than the bare frequency. And that's expected from the ground state properties. Okay? And the second thing is notice this very broad spectrum of inelastic photons coming out all the way down to k equals 0. Right? So that we'd like to understand. And with these kind of schematic diagrams, they're not real diagrams, but just as pictures of what's going on, you can look at the following. So the first is if I only had the random wave, if I made the random wave approximation, this is what would happen, right? I have 2 photons coming in. So the first photon excites the qubit, decay to the ground state. The second photon comes in, excites this qubit, it then decays to the ground state, and the sum total of the energy going out has to be 2k naught. Right? That's the RWA process. On the other hand, if I allow a process beyond RWA, I can have 3 photons come out. So I have 1 photon come in, it excites the 2-level system, the 2-level system decays, I'm in the ground state. Now I do a non-RWA process. So I excite the 2-level system and emit a photon, and then that excited state decays to the ground state, emitting another photon. So there's 1 non-RWA process. I have 3 photons coming out of my system. And the constraint for 3 photons, the constraint given by energy conservation, is of course much, much weaker, right? And allows a whole continuum of outgoing frequencies. So that's what's happening here. This continuum of outgoing frequencies is coming from this non-RWA process. Notice that this non-RWA process, you can think, well, it's very unlikely, but it is the linear response after all, right? This process here is first order in the intensity of the system. It's the linear response which was calculated by the Yale group, for instance, while the RWA only comes in for inelastic scattering at the order of at second order. So it's a nonlinear effect. So as we go to weaker and weaker power, you know that this is going to dominate. The power here, by the way, in the incoming pulse, we had an n bar of 0.5. Okay, so what's the dependence on the coupling strength? So as you would expect, as I increase the coupling strength from 0.1 to 0.2 to 0.3, the inelastic spectrum gets bigger and bigger. It does so in a nonlinear way. Not too exciting. And notice that the peak also shifts to lower and lower value, indicating that the qubit frequency is getting more and more heavily renormalized. So let's compare with the RWA. So on the left-hand side, I have off resonance, and on the right-hand side, on resonance. So in the off resonance case, RWA is the red, and the blue here is the 2-photon, the full result for 2 photons, for the 2-photon component. And you can see that the RWA is getting the 2-photon part correct, right? It's the leading order process for the 2-photon part. But it's a very small fraction, it's a rather small fraction of the total inelastic scattering. So when you're off resonance, the RWA fails very badly for the total inelastic scattering rate. On the other hand, when I'm on resonance, so here's the same result on resonance, and you can see here that the RWA is doing very well. Notice the change in scale. Right? When I'm on resonance, of course, the scattering is much more intense than when I'm off resonance. This is the inelastic scattering. The dotted line is the incoming beam. This is the inelastic scattering here. However, if I zoomed in on this scale, you would see a tail of the inelastic scattering going all the way down to 0, coming from this 1 to 3, 1 photon in, 3 photons out process. So finally, what's a good signature? Or another signature of this is in the photon-photon correlation. So remember, I commented earlier that in RWA, the G2, the intensity of correlation function in reflection must be 0 at t equals 0, right? Because a single qubit can only emit one photon at a time. In RWA, so the light lines here are the RWA curves for G2 as a function of time, they start at 0. But in ultra-strong, I don't have that constraint. Right? I don't have that constraint because there's already photons there in the ground state, in the cloud around the qubit. And so in this scattering process, I can easily have two photons coming out at the same time. So in fact, you see that I have a non-zero intercept. This is for alpha is equal to 0.1. This is for alpha equals 0.2, which can be quite substantial, a half here in this case. And there's other features like this big bump in G2 going over 1 there. Okay, so that's, I wanted to show you the two-particle wave function. So this is, again, the intensity squared as a function of now the coordinates in space. So it's a two-particle wave function. This is my incoming Gaussian state here. And this is the outgoing. And you can see, so this is the sector in which two photons have been transmitted. Here, one is transmitted, one reflected. And this are both reflected. So in the reflected channel, you can see very clearly, right, the anti-bunching. I think this is in the alpha equals 0.1 case here. But you can also see the bunching in the transmitted case, and that this is elongated along this direction, where it's much longer than it is in that direction. Okay, so that's all for the results. Let's talk about future directions a little bit. So first of all, I think that observing and characterizing these correlated photon effects of various sorts, I've only talked about some of them here, is very valuable. And what's the best way to observe them in the various systems that I can. There's the whole quantum information angle, so you can make. We've done some work on quantum key distribution, also a photon qubit pi phase gate is possible. There's a number of sort of quantum information aspects that are being pursued. The ultra-strong coupling regime, has only been really touched briefly in terms of non-equilibrium effects. And finally, there's an issue of suppose I had really a lot, an extended system of these two-level systems, which are strongly coupled to the waveguide. What kind of correlations or what kind of states could you have? So, and with those speculations, I'll close. So I hope I've convinced you that in this problem of having a qubit coupled to a 1D waveguide, there are interesting photon correlations caused by inelastic scattering. The main thing is that this nonlinearity of the qubit causes these photon-photon correlations. I showed you some results for photon statistics by quantum jumps, and showing sort of much more clearly than whether the photons and in what way the photons are bunched or anti-bunched. There's this rather amusing result of photon capture into a bound state in the continuum. In the two qubit case, it led to a long-lasting entanglement between the photons. And then the last part of the talk was, of course, on particle production in the ultra-strong regime. So let me acknowledge all my collaborators, the people who worked on the problem. So 3 students at Duke, Kuai-Shu Zheng, Liu Feng, who just left, and Xin Zhang, who's a current student of mine. I collaborated with a quantum optics experimentalist, Yang Giltier, until he unfortunately left Duke to go to Ohio State. The ultra-strong work is done really in close collaboration with the group in Grenoble, in particular Serge Florent is really key in that. And finally, the bound state in the continuum and non-Markovian work is done in collaboration with Francesco Ciccarello and Giuseppe Calico, and I acknowledge the NSF for funding this work. Thank you very much.
Questions? Let me start with this is simple, kind of just a definition. So I didn't quite exactly get what exactly ultra strong means. So what is the limit from which on you call it ultra strong? Is it just general, the one where you cannot make a rotating wave approximation anymore? Or?
That's the way I use it, yes. And I don't think there's a sharp, I mean, there's not like there's a, sharp transition or anything where that happens. It's just that RWA gets progressively worse, I think, as alpha gets stronger. But it's certainly clear that at alpha equals 0.1, you need to use, I mean, the counter-rotating terms are important.
So for this kind of particle production, what is roughly, do you have I guess there's a limit over which you have to get so that you can see that in principle.
Right. So, yeah, so then I think you have to talk about the detection. Because the idea then is that you would have to detect, this spectrum. So the weight in this spectrum has to be big enough so that you can detect it, and that will tell you what the alpha is. And I have not done that estimate. I'm sorry, so I don't know. I think in the Grenoble experiment, they're expecting alpha of about 0.3, and they expect to be able to see this. Yeah.
So I have a question. So for this analysis, does your ansatz which you use, can you use it to see the phase transition?
No. The ansatz breaks down at the transition. So, I mean, we show that you can go right up, well, almost right up to the transmission, but you would need some additional ingredient in order to capture the doubly degenerate ground state.
But I thought there is an exact solution also for this.
There's an exact solution at alpha equals to 1. There's a beta ansatz solution. Yeah.
But your ansatz does not translate, does not connect.
Well, no. In the ground state properties, you can see alpha equals 1 goes right up there, and we're coming in. If you extrapolate, you can see we're very close.
But alpha equals 1 is phase transition. What's the phase?
No, the phase transition is a little bit beyond it. Yeah. 1 would be the phase transition for delta, the qubit equal to 0. Right? So the qubit frequency isn't equal to 0, so it's a little bit further on. Yeah, it's true.
Any more questions? Otherwise, let's thank Harold again.
Mm-hmm.